Swayam Prabha. Digital India. Educated India.
So today's topic will be transportation problem formulation. Now, you see the transportation problem, what really happens, the materials are transported at minimum possible cost from a set of sources with availabilities to a set of destinations with demands. So here you see we have three different sources, S1, S2 and S3. And there are three different destinations, D1, D2 and D3. Now at each of the sources there are certain availability of material, availability 1, 2, 3, and in each of the destinations there is certain demand. So what you have to do, the material has to be transported from the sources to the destinations. Now obviously source 1 can transport material to D1, D2 or D3. S2 can also do that and S3 can also do that. So in this combination there are 9 possible paths in which the material can be transported. Now each path we assume there is an unit cost of transportation. This is known. All right, so the idea is that how much S1 should transfer to D1, D2 or D3, and same thing about S2 and S3, so that the total cost of transportation is minimum. Now transportation problems are everywhere. One particular example I can give you that is about the, let us say, the coal. So suppose coal is produced, at various collieries. Today, for some time there is, not much of import of coal. But hypothetically, if you assume that import of coal is also allowed, then, there are different ports in the country, and coal is, usually imported from Australia. So, so from Australia, the coal actually arrives at, say, few ports, maybe 2, 3 different ports. And let us say there are 2, 3 different sources of coal from Coal India, like Dhanbad, Asansol, or Neyveli Lignite Corporation from Neyveli near Madras. So you see, there are those kind of sources, and import the landed cost also. If you see, then those ports could be also some transportation availability or sources. The material has to be transported to different locations where coal is being utilized, right? So what should be, how much coal should be procured from, if you look at it, based on their availabilities, so that the demand should be met, right? So like these, there are different kinds of transportation problems that one can really think of. And these are all essentially kind of linear programming problems. So, in a transportation problems, already we discussed the materials are transported, and unit cost is known from every source to every destination. Now, transportation problem in the general form, it can be expressed along with these kind of equations. So first of all, we have to identify the variables. The decision variables are Xij's, quantity transported from source I to destination J. AI is the availability in source I. DJ is the demand at destination J. Cij is the cost of transporting 1 unit of material from source I to destination J. M is the number of sources, N is the number of destinations. So what should be the objective function? See, objective function is for every Xij, that means if every source to every destination, the Cij is the cost component, Xij is the quantity component. Cost is per unit. So Cij, Xij, sum over J, sum over I equal to 1 to M, J equal to 1 to N, that should be minimized. So this much should be clear. That is the objective function. What are the constraints? The constraints are that the quantity that are being transported at every destination, that should be that should be within the availabilities, and the demand should be also met. Is it all right? So basically, this is j equal to 1 to n. That is probably wrong. So what we have to do is that for every sources, the material transported from that point all to different destinations. That is true. That is not wrong then. Two different. See, let's go back to that diagram. Then it will be clear. Then you see, this is from source 1. From source 1, the material is transported to all the 3 destinations. So if you sum them, the total material transported from S1, that should be less than A1. And the demand should be met. That means the total material arriving at D1 should be more than D1. So that is why the constraints are of this type. That sum over j equal to 1 to n xij should be less than equal to ai for all I, and xij should be greater than equal to dj for all j, and xij should be greater than equal to 0. So this is the linear programming formulation. Now before we proceed, can you tell me, suppose you have to solve this, let us say that m is equal to 3 and n is also equal to 3. How many different unknowns are we going? How many unknowns are we going to have? Number of constraints are, that is m into n. What is the number of constraints? Not 9. It will be 6. Why it is 6?
Can you please explain that?
For each source there is a constraint. Each destination there is a constraint. Is it not? So each source, there are 3 sources. So there are 3 constraints from source side. And there are 3 destinations, so 3 constraints from the destination side. Is it all right? So I don't know whether I have written that equation, but I have not written. Anyhow, there are 6 different constraints, that is m plus n. That is the total number of constraints. Now the question is that if you want to solve this linear problem in the usual manner, the augmented problem will have m into n number of unknowns. And also there will be m slack, n surplus and n artificial variables. Can you see that? See, because these constraints, availability constraints are m in number. So there will be m slack variables. The demand constraints are n in number. So there will be n surplus and n artificial variables. So what is the total number of unknowns? Then it is going to be m into n plus m plus 2n. Is it not? So, total number of constraints, total number of unknowns then would be, if m and n both are equal to 3, 9 plus 3, 12 plus 6, 18. There will be as many as 18 unknowns, and there will be 6 different constraints. So you see, the problem is going to be difficult. It will be difficult to solve. So therefore, we make a new constraint we add. What is that constraint we add? Suppose we now add a new constraint, that is total availability at the source equal to total demand at the destination. Right? So total availability at the source and equal to the total demand at the destination. Now it may be true or it may not be true in reality. In reality, there may be availabilities may be more or demand may be more. But for the time being, let us assume they are equal. And what happens if they are equal? You see, what would be its impact? Suppose this is assumed. Then just imagine that if sigma ai and sigma dj's are same, is it possible that all the xij's are less than ai but greater than dj, and sigma ai equal to sigma dj? Is it possible? Is it practical? It is not possible. It is not possible. Just look at these diagram, suppose this is 40, 20, 100, and these are 30, 30, 40. So you see, if everything is less than 40, 40, 20, then the total should be less than 100. So if the total is less than 100 and this side is also 100, how the total can be more than 100? That is not possible. You see, suppose this is less than 40, this is less than 40, this is less than 20. So what happens? Then the total should be less than 100. But also we are saying that this should be greater than 30, this should be greater than 30, this should be greater than 40. That means the total should be more than 100. Now from this side, if the total is less than 100, how can it be more than 100? It is not possible. All right. So if we put this overwhelming condition, that is sigma AI equal to sigma dj, is that constraint is putting us a particular thing, and that particular thing is all the constraints will now turn to equality. Is it not? So if you simply add a new constraint, that is sigma AI equal to sigma dj, that is total availability equal to total demand, that would make a very interesting change in the whole thing. And that change is all the constraints will become equality. Why? That is the answer I gave few minutes back, because we cannot have Xij less than availabilities at the same time Xij more than the demands, because total availability equal to total demand. If the total is 100 on both sides, it cannot be less than 100 in one side and more than 100 in another side. That is not possible. Only solution is both sides should be equal to 100. And that is possible only when sigma Xij equal to Ai and sigma Xij equal to Dj when taken the sum is from other side. Right? So you see what is then going to happen. The problem now transforms to minimize z equal to sum over I sum over j Cij Xij subject to sum over Xij equal to Ai for all I and sum over Xij equal to Dj for all j and Xj greater than equal to 0. Yes, what is the question? I got your question. What you are basically saying that if total availability is not equal to total demand, is it not? What is going to happen then? So what I said in the beginning, that let us assume in the beginning that total availability equal to total demand. You see, if the total availability and total demand they are not equal, then we have some we have to add dummy sources or we have to add dummy destinations. Is it all right? So if the demand is less, then we can add a dummy destination so that they become equal. If the availability is less, then we can add a dummy source, right? So we have to add some dummy source or some dummy destination and make the problem balanced so that this particular thing is possible. All right, so have I answered you? Good. So you see, therefore, a quick recap. So please remember these, originally the problem was one of inequality, right? The general formulation of transportation problem is inequality. That means the sum of Xij over j should be less than Ai and sum of Xij over I should be greater than Dj. So, but then to simplify, we have added a new constraint, and that new constraint is sigma AI equal to sigma dj. That means total availability at the sources equal to total demand at the destinations. When we do that, all the constraint has turned to equality, and we have a new problem, that is minimization of z equal to double sum over I and over j Cij Xij subject to sum over Xij over j equal to Ai for all I and sum over Xij over I is Dj for all j. And obviously all the Xij's are greater than equal to 0. So when we have these equality constraints, then we can think to solve these equality constraints, and number of unknowns are also become much less. The number of unknowns in that case is only m into n. But the question is that how many equations are there and how many unknowns are there? See, total number of equations now are m plus n, and total number of unknowns are m into n. Now m into n is always higher. So suppose m is 4, n equal to 3, then total number of unknowns are 4 into 3, 12, and total number of equations are 4 plus 3, 7. Can you see that? So what really happens then? How many can you solve? See, you have 12 unknowns and 7 equations. So how many can you solve? Yeah, it looks that you can solve 7. But unfortunately, even 7 also you cannot solve. You will be solving 1 less. Can you see why the degree of freedom goes down by 1? Because you also have another constant, that is sigma ai equal to sigma dj. So basically, since sigma ai equal to sigma dj, although you are having 7 equations, out of that their rank is not 7, their rank is only 6, because one equation will be redundant because of the sigma ai equal to sigma dj. Is it all right? So because the total is same on both sides, moment you have 7 constants, only out of the 7, only 6 are going to be independent constants, and at least one constant will be non-independent or a dependent constant. So it will not give any new variable values. So that actually, because of that, we cannot solve m plus n. So once again, total number of unknowns m into n, total number of equality constants m plus n. How many can be solved? Is it m plus n? Answer is no. No, it cannot be, because it will be only m plus n minus 1. Why? Because the additional constant is there, sigma ai equal to sigma dj, and these additional constant will render one constraint as a redundant constraint, and because of that one basic variable will be reduced, and we shall have only, we can solve m plus n minus 1. So therefore you see, for every transportation problem, if m is the number of sources, n is the number of destinations, then number of basic variables will be only m plus n minus 1. Right? We cannot solve m plus n. We can solve only m plus n minus 1. So that we must remember, that only that many can be solved and not more. Right? More number of variables cannot be solved. Only m plus n can be minus 1 can be solved, because the additional constant is also there. Right. So since it is so, then we have to see that certain other things about certain assumptions of the transportation problem. Uh, at least 4 assumptions are here. Let us read them out. The first assumption is that unit production cost is same everywhere. Now, what is an unit production cost? The unit production cost basically comes in that supposing we are minimizing the total cost, here we are only taking the transportation cost, but suppose we also see that different sources, the cost of the product is not same. Suppose the cost of the product is different at different sources. So if that is to be taken into account also, then there will be not transportation cost alone, but sometimes you may have to take the production cost also. In fact, a problem is very interesting. A particular company charges only, let us say, loading and unloading costs. It doesn't charge the transportation cost. So all you have to do is to transport material from a source to the another destination, total cost per unit would be loading cost plus the unloading cost only. Is it not? So those kind of things are to be looked into. And also you have to see that problem we are solving from whose point of view. Because if we have to think the problem from the transport company's point of view, then everything they get is going to be their gain. So that problem will be one of maximization because that is the charge they are getting. But if you are looking at it from the other, that means the transporter's point, I mean, transporting company, that means the company that is whose material is being transported, then that is a cost minimization. So one has to be careful about those things also. Then transportation costs need not vary directly as the distance. Rather, an unit cost of transportation is specified for each source to each destination. Is it not? So it is not proportional to the distance. We are just putting an unit cost of transportation. Then the third constant is very important. There is no transshipment. You see, a transshipment is a very important term. Now there are many types of transshipment. One transshipment type is there are intermediate nodes. So we have the sources, maybe a few sources. Material is sent to the destination. So one source to the one destination, but maybe there are intermediate nodes, right? From different sources, the material comes to a mother go down. From mother go down, you again supply the material. So, that is also possible. So that is one kind of transshipment. The material comes from different sources to some intermediate node, and then from the intermediate node, the material goes to the destinations. Other kind of transshipment could be source to source. You see, currently we are saying that, let me get that diagram. Currently we are saying that the flow of material is from source to destination, source to destination, source to destination. But suppose we say that we send some material from source 1 to source 2 and then transport to D1. We don't send anything directly from S1 to D1, but S1 material we send to S2, and then from S2 to we send the D1. Maybe S2 to D1 is less costly, and even when you add S1 to S2 transportation, even then that cost is less. So that could be an option, that S1 to S2 to D1. So that is one kind of transshipment. Another kind of transshipment could be you send the material from S1 to D1 and then from there you transfer to D2, right? So destination to destination transfer. Sometimes even destination to source. Maybe from S1 you send material to D1, from D1 you send to S3, and then from S3 you send to D3. That looks a little too much, but anyhow, practically that is also could be an option. Is it all right? So source to destination to source to destination. So that means when normal transportation is only source to destination, transshipment could be source to source also, or destination to destination, or destination to source. So that means when there are transshipment, the possibilities are source to destination, source to source, destination to destination, destination to source, or source to some intermediate node, and from intermediate node to the destination. So all those could be different types of what you call transshipment. So is it clear that what are the different kinds of transshipment? Initially, our assumption is that there is no transshipment. Is it all right? So there is no transshipment. So there are no intermediate nodes and no movement from source to source or destination to destination or destination to source is allowed. And then finally, there is no restriction in any supply from a source to a destination. Sometimes these also could be a reason. Sometimes what happens that we say that no, say for example, the coal is available from BCCL, that is from Dhanbad. Coal is also available at ECL, that is the Asansol area, and the coal is also available in the Neyveli lignite area. Now all the coal is not same. The coal that is available in the eastern region of the country, they are mainly the anthracite or the bituminous coal. They are much better coal compared to the lignites which are available at Neyveli lignite. So you see the lignite as a coal is a much poorer coal, and anthracite is a much better coal, and those kind of coals are only available in the eastern region of the country. So therefore, you see, one may say that look here, we want coal only from the BCCL or from ECL, and we don't want any coal from the Near Valley lignite, that is NLC. All right. So all these are different other kind of constraints that there could be restrictions from supply to a source to a destination, right? Initially, we assume that there is no such restrictions. So there are different assumptions. The unit production cost is same everywhere. Transportation cost is constant. That is an unit cost of transportation. There is no transshipment, and there is no restriction in any supply from a source to a destination. So all the four constraints are understood. Additionally, there is also a new constraint we have added, sigma AI equal to sigma dj. Is it not? So these are some of the key assumptions of the transportation problem.
Excuse me, sir.
Yes, yes. Tell me, please.
Sir, can you please explain the third assumption?
Transshipment.
Yes, sir.
Okay. So once again, what is transshipment? We shall do, see, we shall have one full class on transshipment, right? We shall discuss different problems on transshipment, and for each of those restrictions, we shall, when we relax these restrictions, what we shall do, we shall take up specific problems for each of them. Is it all right? So there will be some transshipment problems we shall take up. And when you solve those transshipment problem, you see that normally, supposing transshipment options are not available, then you only transfer material from the source to destinations. But when transshipment options are available, then you can send material from source to source, and then from there to destination. Maybe you might get some advantage depending on the costs that are available from source to source or destination to destination. In fact, transshipment problems, when you solve, you can actually solve different kinds of flow networks also by the transshipment algorithm. All right, maybe some of these things are not very clear right in the beginning, but it will be very clear when you actually solve the transshipment problems. Is it all right? So let us proceed. And as we move further, maybe your very clear answer you shall get. Now, transportation problem as a linear programming problem. The transportation problem is a special case of linear programming. The coefficient matrix values are all ones in a transportation problem. So we have seen that simplex tables and the coefficient matrix values. So here the coefficient matrix values are all one. Because the transportation problem is a special case of linear programming, it can be solved by the transportation algorithm. The transportation algorithm is simpler than the simplex algorithm. Attempting to solve transportation problems by the simplex algorithm would be cumbersome because there will be degenerate solutions. All right, invariably there will be too many zeros if you are trying to solve transportation problems by the simplex algorithm. So we have to have a separate transportation algorithm, and then we shall let us look at it by an example. So here is that example, and in that example, if you look at, first of all, there are three sources. Basically, there are three factories, and there are four destinations, which are called four warehouses. So F1, F2, F3. The availabilities in the three factories are 11, 13, and 19. So that total availability is 43, right? 19 plus 13 plus 11. And what is the total demand? Demand at warehouse 1 is 6, warehouse 2 is 10, warehouse 3 is 12, and warehouse 4 is 15. So what is the total demand? It is also 6 plus 10, 16 plus 12 plus 15, 43. So you see the first check has been made, that sigma AI equal to sigma dj. So this side is sigma AI, this side is sigma dj, and both sides are equal. So this is 43. Other things that we need to know the input, the unit transportation costs. So to transport 1 unit of material from F1 to W1, the cost is 21 maybe rupees per unit. Here it is 16, 25, 13 and other values are also there. Right. Now to solve transportation problems, we must have a quick initial solution. So there are different methods by which a quick initial solution can be obtained. There are Vogel's method, and there are method which is about the different costs that we can see the difference in costs and all that. And a very quick method is called the northwest corner rule. All right, so let us see that by northwest corner rule, how can we get a quick solution? So what is the northwest corner rule? Northwest corner rule is, see, this side is north and this side is west, right? So west is this side, north is this side. So, that means this is the northwest corner. So we make some entry as much as possible in the northwest corner. So you see this side total is 6, this side total is 11. So maximum value that we can put here is 6. All right. So that is what we do in northwest corner rule, that maximum value that we can put in the northwest corner, that is 6. So we put a 6 here and we put crosses because nothing more can be entered here. So this is 6 is entered. So rule is begin at the northwest corner, allocate as much as possible, continue south or east till m plus n minus 1 entries are made. Then we move this side because this side is not possible. So in this side, you now see this is 10 and this is 11. Now enter of 6 is already there, so only 5 more can be entered. So that means 6 and 5, and there should be cross. So then this side we cannot go, then we go downside. So obviously this side if you go, then the total is 10 and from this side the total is 13. So 5 can be entered. So again we put a cross here. Then we see we go this side, this side total is 12, this side total is 13, 5 is already there. So we put a 8. And then we put a 4 here and 15. So is it clear that how we got these entries by the northwest corner rule? So because I have uploaded the file, but anyhow, please, okay, anyhow, I'm telling the values. So you see this 6, can you see the 6? So initially that this is the northwest corner. So, this northwest corner, we put a value of 6, right? So this value of 6 is put first, and after the putting the value of 6, then we go to the, we see that this 6 is exhausted. The total demand was 6, so that is exhausted. So therefore from that 6 we have to go the other direction. So when you go to the other direction, there you find that maximum possible entry that is possible is 5. All right, because this side total is 10. So then we make an entry of 5 there. Then we go this way because that side is exhausted. So when we go this way, that is downwards, then here the total is 13 and here the total is 10. So 5 is already allocated. So remaining 5 we can allocate. So we put a 5 there, and thereafter we go this side, and then we could make an entry of 8 because 12 is total this side, 13 is total this side, 5 is exhausted. So we make an entry of 8, and thereafter we go downwards, and then total is 12. So we make an entry of 4, and finally we make the remaining entry 15 so that both sides are exhausted. So look here, number of factories are 3, number of warehouses are 4. So M is 3, N is 4. So how much is M plus N minus 1? M plus N minus 1 is then 7, isn't it? 3 plus 4, 7 minus 1 equal to 6. So that means total number of basic variables should be 6. How many basic variables are there? 1, 2, 3, 4, 6. Clear? So that is how the northwest corner rule finds an initial solution. So what is the total cost of this initial solution? 6 into 21, 5 into 16, 5 into 18, 8 into 14, 4 into 18, 15 into 41. Anyhow, whatever that value,
Excuse me,
that is
sir.
that. Yes, yes. Number of basic variables. See, there are 7 equations here. Can you see that? That
Yes.
total number of factories, total availability 11, 13, 19, and 6, 10, 12, and 15. So total there should be 7 different equations to fulfill.
Right, sir.
But out of those 7, only 6 are possible to find because of additional constraint sigma ai equal to sigma dj. Because both side total are equal. So you see at the last when we wrote 15, both sides are simultaneously satisfied. Why it happened? Because of the reason that total demand equal to total availability. Is it not? So that is why only one less we are going to get, and total number of basic variables will be only 7 minus 1, that is 6. Is it
Okay,
all
sir.
right? So
Yes.
totally we have 6 different entries, and they are our initial solution. Then we see that this initial solution is optimal or not. So in order to do that, we have to compute the Cj minus Zj values. Now, how do you find out the Cj minus Zj values? So there is a method. The method is called the UV method. What is the UV method? Already, last class, if you remember, we talked about the dual variables, which are like node potentials. Now, the UV method is nothing but the same method. In fact, these UVs are nothing but the dual variables. But here the rule is made slightly simple. And instead of UI minus Vj, we are making UI plus Vj. And so that the Vjs are like negative of the node potentials. So in that sense, what we can do, consider UIs for the sources or the factories and VJs for the destinations or the warehouses. Now for the basic variables, UI plus VJ equal to Cij. Since there are m plus n minus 1 basic variables, we have m plus n unknowns and m plus n minus 1 equations, because you see there are ui and vj, m number of u's and n number of j's. So total is 7. So we have uh, m plus n, that is ui and vj, but since only basic variables are only 6 in number, so therefore number of equations are going to be 6, but unknown 4 number of UIs and 3 number of, look at here, the 3 number of UIs and 4 number of VJs. So total there are 7 number of different unknowns to solve from these equations. But what we can do, you can always, because their relative values are important, so you can start with one of the UIs or VJs as zeros, and this will not be a problem since only relative values are important. So one example I'll show you, then it will be clear to you. Now for the non-basic variables, compute Cj minus Zj as Cj minus Ui minus Vj. All right, so once again, we'll come back to this slide. So let's look at how these computations are made. So computations are made in this way. Say for the basic, see these are basic variables. For the basic variables, ui plus vj should be equal to cij, right? So these are the 6 basic variables, and there are 7 unknowns, 3 UIs and 4 VJs. So let us see how they are computed. So first of all, we put one of them as 0. Let us say U2 equal to 0. So you see U2 equal to 0 when we put, then this basic variable, the cost is 18. So V2 should be 18, because U2 plus V2 should be equal to this F2W2 square total cost, because UI plus VJ equal to Cij. So that means 0 plus 18 is 18 here. Now similarly here, this is 14. So UI plus VJ will be 0 plus 14. So it should be 14. right? So that would give V3 equal to 14. So we found that U2 equal to 0, V2 equal to 18, and V3 equal to 14. Now look here, we have here 18. So V3 is 14. So that would give U3 equal to 4 because 4 plus 14 equal to 18. Again, we have got this V2 equal to 18 and total is 16. So that would give U1 equal to minus 2. Right? So once you have U2 1 equal to minus 2 and this total is 21. So that would give V1 equal to 23. And finally, U3 equal to 4 we already got. So since this total is 41, that would give V4 equal to 37. So have you understood that how UIs and VJs are computed? Supposing U2 equal to 0. Now here what we exactly we wrote that for the basic variables UI plus VJ should be equal to Cij. Is it not? Now, since there are m plus n and my one basic C, how many equations we shall get? We shall get, because there are 6 number of basic variables, we shall get 6 number of such equations. But how many are to be solved? 7. So we cannot solve 7, we can solve 6 only. So one of them we have to arbitrarily put at 0 to begin with. This will not be a problem since only relative values are important. Relative means their sum is important. So non-basic variable would be Cj minus Zj would be Cj minus Ui plus Vj. So for non-basic variables Ui plus Vj equal to Zj or Zij, and for the basic variables Ui plus Vj equal to Cij. Is it all right? So Cij minus Zij can be, or I mean I wrote Cj minus Zj. Truly speaking, it should be Cij minus Zij. Right. So once again, let us compute. So we started with U2 equal to 0. Right. So if you start with U2 equal to 0, you know that U2 plus V2 should be 18. You know why? Because U2 Ui plus Vj should be equal to Cij. That is the cost. So this much if you know, then if you arbitrarily start U2 with 0, then you can write V2 equal to 18 and V3 equal to 14. Is it clear to all of you? Because if U2 equal to 0 and U2 plus V2 equal to 18, then V2 should be 18. Yes or no? So since U2 equal to 0, it will also give V3 equal to 14. All right. So that V3 is also obtained. So now we have got 3 of them, U2, V2 and V3. Now look here, the V2 we got 18 and this total is 16. So then U1 should be minus 2 because minus 2 plus 18 should be 16. All right. So using the basic variables, we are computing the UIs and VJs. Since U1 is minus 2, that would put V1 is 23 because this is a basic variable and minus 2 plus 23 is 21. All right. Similarly, because we got V3 equal to 14 and this total is 18. So U3 we can then write 4. And since U3 we have written 4 and this total is 41. So you can then write V4 equal to 37. So like this you can compute. Now I started arbitrarily U2 equal to 0. You can also start U1 equal to 0 or U3 equal to 0 or V1 equal to 0. Any one of them you can start at 0. You will get another set of values, but then the UI plus Vj total will be same. Right, that you must remember because it is the total that is important. All right, so then we can compute Cj minus Zj for F1 W4. What it will be? It will be 13 minus of minus 2 minus 37. So it is minus 22. What will be the Cj minus Zj here? 23 minus 0 minus 37. So minus 14. And these are plus, this is minus 6, 17 minus 0 minus 23. And this one 32 minus 4 minus 23. So it is a plus. Plus means we don't compute anymore because that we are not interested in this square. So 27 minus 4 minus 18, that is also plus. So, Cj minus Zj values are then computed for the non-basic variables. So 1, 2, 3, 4, 5, all the this is also plus 25 minus minus 2 minus 14. So we found out the Cj minus Zj values. So is the Cj minus Zj value computation is clear to you? So if you that is clear, then tell me which is that square which is the most favorable square which will reduce the total cost. Which variable should now enter into the basis? F1 W4, because that is having the low minus 22, that is the lowest possible value. So that means some entry will be made in F1 W4. Now the question is, if some entry has to be made here, then it has to be balanced against this square. That means those basic values should be appropriately adjusted. So how it will be adjusted? A closure has to be obtained, and this closure is very important to obtain. So look here how the closure is obtained. Look here, if an increase is made here, something has to decrease along this column. So only one square is available. So that means this 15 should decrease. If this 15 decreases, something should go up. That means this 4 should go up because there is nothing else. If this 4 goes up, something should go down. That means this 8 should go down. If this 8 goes down, something should go up. That means this 5. So 5 should go down up. And this 5 goes up, then something should go down. That means this 5 should go down. And then that would balance with the original. So now you can see that closure is obtained. So look here, this closure we have to find out every time we make an entry. So that means which one is going to be our entering variable? F1 W4. Which one should be our leaving variable? Which is the least amount? That is F1 W2. Because look here, 8 is, even if we deduct 5, it is still a positive quantity. This 4 is a low number, but it is going up. So this 5 is a low number, but also it is going up. So this 5 is therefore is the leaving variable. So in a sense, this 5 will come here. This 15 will become 10. This 4 will become 9. This 8 will become 3. And this 5 will become 10. So look here how the closure is obtained and how the new basic variables, the next iteration, that is the next table, can be obtained. So is it clear? So please go through this diagram very carefully and convince yourself why the changes are going to happen the way I have explained. First, you understand the closure. Is the closure understood? Is the closure understood? Yes, that means look here that first we make some entry here. As you make some entry, that means if we increase something, something has to go down. So this 15 has to go down in the column wise. Row wise, we don't know which one because there is a tie. There are two variables. So forget row. Go to column wise. Column wise, we see that if we make some entry here, something goes down. So that means this 15 has to go down because there is nothing else to go down. And if this goes down, this goes up, this goes up, this goes down, this goes down, this goes up, this goes up, this goes down. So now closure is obtained. All right. So this closure, if you understood first, then we have to see out of everything that is going down, what is the lowest? Which is the lowest one that is going down? Lowest one is F1 W2, isn't it? Lowest that is going down, there are three things that are going down, 5, 8 and 15. Rest are going up. So this 5 is the least that is going down. That means this entry will be not there anymore. In a sense that F1 W2 will be the leaving variable and F1 W4 will be the entering variable. And in the new table, this will be not there. This will be 5. This 5 will become 10. This 8 will become 3. This 4 will become 9. And this 15 will become 10. All right. So you see see how the closure is obtained. This is important. There should be non-basic entry cell and all the rest should be basic variable. Right? And maximum possible entry at F1 W4 would be 5 because that is the maximum that can be reduced. So with that, we can say that this 5 comes here, this 5 becomes 10, this 8 becomes 3, this 4 becomes 9, and this 15 becomes 10. All right, so that is what we have done here, and the new table is obtained. So 6, 5, 10, 3, and 9 and 10. Is it clear? So that is how we get the second iteration with the UV coefficients. Is it clear? Have you understood that how we got the second table? That is the second iteration. Is it not? So again, we have to compute the UV coefficients. Once again, we put U2 equal to 0. And since these are 18 and 14, so these 18 and 14 are written. Now using this 14, because it is 18, we get this 4. Using this 4 and 41, we get this 37. Using this 37 and this 13, we get the minus 24. And using all of them, we again compute the Cj minus Zj, because 17 minus 0 minus 45 is minus 28. So like these, all the coefficients are computed. So where we can make some entry now? It should be F2W1, is it not? So in the next, then we make some entry in the F2W1 cell. And as you make those entries, further closure is obtained. Yes, you have to calculate U2, U3 and all those things again. Again, you have assumed U2 equal to 0, and based on which V2 become 18, because this is a basic variable, V3 become 14, and because V3 has become 14 and this is 18, so this becomes 4, this 4 and 41, so this becomes 37, and this is 13, so this becomes minus 24, and this is 21, so this becomes 45. So you can always cross check by recalculating with those basic variables, and thereafter we can compute for the non-basic variables. So this was 17, so 17 minus 0 minus 45 minus 28, like that. So like this, for all the square non-basic variables, you have to compute Cj, Cij minus Ui minus Vj, and for the basic variables, Ui plus Vj equal to Cij. And to begin with, you have to assume one of the variables as zeros. So like this, the process has to continue, and so that ultimately, if we get everything positive, and that is where we stop. Is it all right? So what I do, I stop here today, and I request you to go through and try to solve this problem yourself, so that at least one more step you make, and so that you try to get the final solution, right? So you have understood the method, how to begin. We have begin with the northwest corner rule, and thereafter we use the UV method to compute the UIs and VJs. Using these UIs and VJs, we compute the Cj minus Zj or Cij minus Zij values, and we make some entry. We find the closure, and using the closure, we go to the next iteration. Right? So is it clear to all of you? Good. So thank you for